There is nothing else that should stop me from introducing Vandana Desai, who will give us an invited talk about enabling the next generation science investigations with the NASA Astrophysics Archives.
So my name is Vandana Desai, and I'm the science lead for the NASA IPAC Infrared Science Archive. I'm going to be talking to you about plans among the NASA Astrophysics Archives for new tools to enable the next generation of science with NASA data. And even though I'm the science lead for URSA, I'm giving this talk on behalf of the other NASA mission archives. So the equal co-authors really are Steve Groom, Tess Jaffe, Eva Momcheva, Josh Peak, Harry Teplitz, and Alan Smale. Okay, so some of you may not be aware of the organization of the NASA Astrophysics Archives, and it's a little bit important for understanding what our plans are. So the archives are distributed in different cities based roughly on wavelength regime. So HESARC serves NASA's high energy astrophysics data from Maryland. URSA serves much of NASA's infrared and submillimeter data from Pasadena, California. And MAST serves mostly UV and optical data also from Maryland, but at a different place than HESARC. Now, even though these NASA has decided to distribute the data into different locations, this of course doesn't have much to do with how astronomers use the data. So for instance, in this really simple example, you see a picture that has combined data from NASA's great observatories, including Chandra, Spitzer, and Hubble, to make one image that gives you a lot more information than you would have if you used any single one of those data sets. There are reasons that NASA has chosen to do it this way. A really important reason is that it allows expertise from the missions to sort of accumulate at the archive centers and to be retained. And this expertise is really, really important for correctly serving the data. Ingesting it takes knowledge to get the metadata correct, and then staffing things like the help desk, which we found is really important for getting out science. Okay, so we started thinking, we are in a distributed data environment where the data sets are starting to get quite large and complex. How are we going to proceed in the future? And it has been sort of a consensus that the direction to go is science platforms. So science platforms have lots of different definitions in detail, but in what they have in common is that they are a place where a user, researcher can log in and do analysis and have access to analysis tools close to at least some data. I'll talk about the practicalities of having it close to all of the data that you might want. So in preparation for the decadal survey, authors from a large variety of institutions, both in the US and internationally, got together to think about this problem. And we wrote a white paper called A Science Platform Network to Facilitate Astrophysics in the 2020s. We knew that we couldn't necessarily all get together and build one giant science platform, but we knew that we needed to serve astronomers who wanted to use data from lots of institutions. And so we wanted to emphasize the fact that different science platforms need to work cohesively as a network. So at that time, which was last year, we, the authors, we made a list of the science platforms that we were involved in that were either in existence and having users already or in development. And so you can see there's a list here. This list has a variety of funding sources. So you see the three NASA archives that I already mentioned. Also in the US, from different funding agencies are systems such as that planned by LSST and Noir Lab and SciServer. And then internationally, we had authors from CanFAR, so from Canada, and ESA, all building different systems. The existence of these systems has been really important because it is, the ones that are operational are really letting us learn what users need, what's working, what's not working. And as one example, I wanted to show this slide that was generated by people at MAST. So they put some data on the cloud and made it available for analysis there using AWS. And they had it going for a couple of years. And this plot shows the monthly volume of access data for two observatories, HST and for TESS. And the first thing you can see is that there's a lot of variation in the volume of access data. And of course, this is an argument for going to something like the cloud, where you can really turn up and turn down your resource without paying for it all of the time. And the second thing you see is that quite frequently, you are seeing monthly volumes that exceed a petabyte or approach a petabyte. And that's really pretty amazing, because the average archive download volume through the normal, traditional web interfaces is far lower than that. And so this is pointing to the fact that when we provide a service like this, analysis near the data, people really take advantage of it, and they're probably doing something quite different than what they were doing with the traditional interfaces, or else people are finding a new way to do use cases. Okay, so the white paper had 3 basic recommendations. One is funding. The funding has to be for software, user storage and computing, operating costs, but also coordination. If we want to have the network work really seamlessly or in a way that's really useful to users, then these science platforms have to be coordinated to some degree. That coordination will maximize the ability of users to be able to collaborate across science platforms, and to make the science platforms truly interoperable, where you can you can be near one, you can do your analysis near one data set, but still be able to combine it with data that is in a different location. And then we also brought up the challenge of actually paying for cloud resources. And we felt that the ability of individual archives to negotiate cloud costs is more limited than it would be if it were negotiated at a higher level, say not the NASA Archives, but NASA or Astrophysics or NASA SMD. So fast forwarding a little bit to earlier this year, the NASA Astrophysics Archives underwent a programmatic review where we all proposed science platforms operating under this science platform network ideal. And we received feedback, I have to move, that having the archives collaborate on a single unified science platform under unified funding is a more likely path to true interoperability. And so this is the strategy that we are now exploring. Rather than having 3 rows on this table have different interoperable science platforms, ours would collapse into 1 row, and that perhaps will result in some efficiencies for NASA. However, I want to stress that there are still many rows left in this table. And as much as we might wish it, we cannot have all of the data that an astronomer might want to use under a single unified science platform. The practicalities of that are just, they will never be, they will never escape from that. Okay, so the exercise that we did to try and figure out what it is that we need to build is we ask ourselves, what will the needs of the community be in 2030? So that's what we're building towards. Okay, so this is a plot from the white paper. We see the data volume of a variety of astronomy missions over the years. And the general feature that we see is that, there's a big difference between 2030 and 1980. That's not very controversial statement. The data volume has grown substantially and will grow. So in 2030, the Euclid mission will be complete if it's not extended, as will SphereX. JWST, Roman, and NEO surveillance mission will still be operating. And there may be missions in development then that we don't know about now. Rubin LSST will still be operating. It's not NASA, but obviously it's a very large data set. And it's important to recall that legacy data will still be in use. And this talk is very focused on NASA data. I understand that there are many of you involved in missions that are not listed here and are not on the chart, but the trends are still the same. Okay, so how will people be looking at those data in 2030? Well, we know that machine learning is going to be an important part of the picture. The plot on the right shows the mentions machine learning in the refereed astronomical literature over the past decade or so. And the trend is, projected out to 2030, everybody's going to be using machine learning. It's going to be super important. We also know that even outside of machine learning, people are going to be wanting to conduct more sophisticated statistical analyses. We're already seeing that journal articles are having separate statistical referees. It is, with great power comes great responsibility. Big data sets are going to demand a higher bar of statistics. We know that joint analyses of different data sets is going to be important. We already see that now, but in the future, missions like Euclid and Roman and LSST are going to raise the bar for how data are combined. It will probably be on the pixel level, not just on the catalog level. So that is going to incur a great demand for both storage and computing. And then co-analysis of simulations with observations is going to be another thing that people are going to be doing more frequently. In fact, the missions are more frequently now creating simulations that are going to be necessary to analyze alongside the observations. And then I want to point out again that archival analysis will continue. We see that data are used for missions well after the missions are complete. And in fact, the usage tends to go up quite a bit. This plot at the bottom of this slide shows the fraction of archival papers for 3 missions, Chandra, Hubble, and Spitzer, as a function of time. By archival paper, I just mean it's a refereed paper that used archival data, meaning that the PI of the initial program was not involved. So you can see that very quickly, even during the operating years of the mission, the fraction of archival papers exceeds 50%. So most of the science is coming not from the PIs, but from people who figure out novel ways of using the data after the fact. Those kinds of analyses often require code that was written during the mission or earlier in the mission. And that's something that we need to keep in mind. It's not all going to be sophisticated, statistical analyses and machine learnings and new. We're going to have to work on preserving the older stuff, the oldies but goodies. Okay, and then I think it's important to look at what the expectations are going to be of not only the researchers, but also the developers and the funding agencies. So NASA has recently added inclusion as one of its core values. And inclusion doesn't just refer to the inclusion within the workplace. I think it can be, for the archives, it can mean including the entire research community. We want to make sure that we are not simply creating tools for the 1% power users, which does include many of the people who attend this conference. We need to be really connecting with people, not just at Research One institutions, but at smaller institutions. We need to be providing tools for beginners and for people who are being trained. Researchers everywhere are going to be expecting a higher level of collaboration and sharing in their tools. Almost everybody uses something that uses that feature already, like Google Drive or Overleaf or Slack. We can't build something that doesn't have that built in, or people really aren't gonna like it. Users have been very successful at contributing data that enhance the science legacy of missions and telescopes. We've found, and MAST has found, that, so URSA and MAST have found that when users take raw mission data and reduce it and make high-level products and then contribute it back to the archives, those enhanced data products have a very high level of publications resulting. I found that, I think if those of you who saw Kelly Cruz's talk yesterday have found that open source software has been a very successful way of sharing software, and increasingly, and typically it's been done between users sort of in an organic way, say with AstroPy, but it's possible that we can actually take advantage of this community at higher levels that are also actually funded. And then finally, there's a growing desire amongst developers and funding agencies for efficiency reasons to increase the amount that we share and learn from other institutions outside of astronomy, including industry. It's a really fast moving field out there. There's a lot that we can take advantage of. We don't need to reinvent the wheel. And also from the greater research community is now helping us in astrophysics of having discussions with people who are very familiar with the Earth science systems. And I think that's going to be a very promising route to go in the future. Okay, and then again, I want to drive home this point that the archive workforce is essential to the science impact of NASA missions. So the National Research Council, way back in 2007, wrote a report called Portals to the Universe, the NASA Astronomy Science Centers, and they concluded that successful research using archival data sets is dependent on the resident expertise and corporate memory that reside at the science centers. So this is really arguing against simply just creating a place where you throw data and then have people, pick through it and find is really important, as well as the documentation and the help desk that all of the archives run. We did a survey of users that showed that surprisingly, one of the biggest obstacles for people doing their science, it wasn't actually, I have a hard time getting my data. It was, I have a hard time understanding my data. I have a hard time finding the documentation and understanding the documentation. So that's the key to, we can't forget that when we focus on the questions. Okay, so our vision for a future NASA Astrophysics Science platform. And I want to just emphasize that these are not solid plans. This is what we're discussing now. And we really wanted to widen the discussion and get more people involved. So there are three essential components. One is a cloud-based interface and supporting system that is really based on open source research software. Two, we want to make this easy to use for people. So we think it's important to have a large collection of notebooks that show people how to use the data and the system, and then also really well-curated software containers that give people a sort of a running start on how to use the multi-wavelength and big data science tools that we will be making available. And then finally, we really need to think hard about the kind of data services that we want to provide. Of course, we already are all in on the VO standards, but in the new system, we may find that the use cases that it enables will require a new set of really fast data services, and they have to be location agnostic, even though the NASA Astrophysics Archives are working together to build will be in one place or even one cloud. And then, of course, we know that people all over the world have interesting data that people are going to want to combine with NASA data. So this is very important it still retains some of that network flavor that I was talking about before. Okay, so
here's
taking
your
each of these
check mark.
in a little more. Okay, taking each of these in more detail, we do plan to borrow from existing systems that combine Jupyter frameworks and open source systems for the cloud. So Pangeo is a system that is from Earth Sciences and has been very successful there. They have much higher data volumes and so are ahead of us in confronting this problem. And there's no reason to reinvent the wheel. We can borrow their system, but then improve it. We will build the system as code on the cloud that will allow us to work together in a very convenient way. But the really cool thing about it is that because it's built as code, you could deploy it. Any one of you could deploy it with a little work and reuse it. And then you would just add your own cloud compute. So different groups can take advantage of this. We plan to make it open. Okay, so the second item is a rich collection of notebooks and software containers. It's hard to find pictures for notebooks and software containers. So the fact is that there are a few users that are really well versed in the software tools that are used across wavelengths, but in the big data regimes, and we can provide notebooks that will teach novice users quickly. And then as people, as an open source environment, you can get really quick evolving code bases. And then we also have those legacy codes that I was talking to you about before. Those can be a real pain to install, especially when you're installing them, a whole bunch of them. If we can be smart and offer software containers that are really well curated, we can lower the startup costs to astronomers. So that's going to be a big part of our solution. And then finally, I'm going back to those APIs. So the IVOA has made a lot of progress. Well, the IVOA has defined many protocols, and NASA is been in recent years really committed to enabling those at the NASA Astrophysics Archives. And so we have a group called NAVO, which has membership by URSA, MASS, NED, and HESARC, and we work together to make sure that we're coordinating our VO implementations. As we go into this science platform era, we may find that users need something different than the existing protocols. Maybe simple image access isn't going to cut it for the kinds of forced photometry, large-scale forced photometry that a user is going to want to carry out in a science platform across wavelengths that may not be co-located. And so we would like, through NAVO to work with the IVOA and the greater community to identify these use cases where existing protocols may be insufficient and work with the IVOA to see how we can solve that problem in, an actual implementation as experiment, as a breeding ground for learning. Okay, so in summary, there are just some points I want to stress that archives need to have with relevant science and mission expertise, and that we don't want to sort of leaves users on their own. We want to build a system that acknowledges that all data of interest will never be co-located. And we envision a science platform that could be designed to enable science from distributed NASA data centers. And I say envision because we are still working on the plan. But part of this plan, I think really importantly, will require coordination to support that network of science platforms. And that's going to be the only way that we can truly meet the needs of a community that really want data from a variety of sources. And that's it. So if anybody has any questions.
Thank you. I don't know where the other applause is, but thank you very much. We have a few questions. Let me open one question by myself. Since I'm the chair, I can do that. I know that there is a software.nasa.gov and codes.nasa.gov. Are there going to be new portals for software, as I sort of seem to see what you're planning to do, or what is going to happen to that? How is the software organized?
So I don't have an answer for that. That is something that we haven't completely solved yet. We have sort of the concepts in line. I've actually, we're just not there yet.
Okay, no,
but
that's fine. That's
it
fine.
is a tricky problem. Software is always the hardest. Right now, I can tell you what we do now. The archives operate pretty, okay. Are you saying that's fine, I should stop, or that's fine, I should go on?
No, because I'm actually very impressed that there is 2 code archives at NASA where you can go and find source codes.
Yeah, and I was going to say that I have never actually even seen those. So I think, yeah, they're very different from.
All right, so we have already 2 questions. Let me go to that. So one question is, in the US and in Europe, space data archives and ground-based archives are somehow disconnected. This artificial separation is often due to different funding sources and are counterproductive when looking at science platforms. Are there plans to unify space and ground-based archives?
So the plans that I am aware of do not at any high level, not plans among the funding agencies that I'm aware of. This is something that we've been talking to NASA about, and that we're really stressing. There are that is actually why we asked specifically for funding for coordination. So we can do the coordination sort of organically because we know it's needed, but of course it will be much more successful if the funding agencies put some, mandate behind it. For now, it's been very informal, and this is something that we need to push on.
Okay. And then Francois would really like to know if you could give an example where the IVOA protocols differ from the NASA archives needs.
So right now, that's something that's under investigation. We sort of have a sense that this might be an area where there could be new needs that we haven't really foreseen yet. What we're doing right now is we have development science platforms sort of internally that we've made separately, and we're starting to let people internally play with them so that they can help us answer that question. But one example that we've had so far is what if I wanted to do force photometry on, I don't know, WISE data and GALAX data? And it's not the best example, but something from URSA and something from MAST, say. Would you do simple image access to pull things over one at a time? No, probably not. With URLs, what happens when there are, object stores? I just think that it's a problem where I can't give you a specific example that's the definite, oh, we need a new protocol, but I can tell you that I can't tell you that we don't need one. This is something where we need to let the scientists play and tell us what they need. So it's an area of work, not an answer.
Oh, we have a bunch of more questions. Nick is asking, how does the interface with the European Escape VO Science Platform Initiative? Any interoperability in terms of user access, logins, etc.?
I'm not sure I understand the question about the first part of the question. In terms of user access and logins, yes, we've talked about having some sort of federated access, at least within the NASA archives. And again, I think we really need to start these discussions to figure out how federated they can be. Can they cross platforms, cross countries, cross funding agencies? As you know, well, I don't know if you know, but NASA has a lot of security requirements. So again, these are things that need to be worked out. I'm not really too familiar with the EU Escape VO Science Platform Initiative. I would like to learn.
Yeah, and I think this will be the final question. Paul is asking, In my experience, much of the data analysis software is designed for the analysis of just a few objects and not for the analysis of millions of objects. Is there a plan to address this deficiency?
I think this is a really important point. This is something that we're already up against at URSA. We have all these web tools where the default search screen is put in a position to search, 100 billion row table. And that's not what people want to do, even at a basic level of just searching. And then you're right that, every use case is going to require at the catalog level, like many millions of rows. People don't necessarily care where they are on the sky. We do need to have faster software. To me right now, that's the biggest issue, is that it just takes too long to experiment. It's hard to scale up. And so, yes, I think this is an important part of what goes in those curated software containers.
All right. Thank you very much.